Welcome to today's episode. We're diving into the fascinating world of distributed systems, with a particular focus on a concept that's vital for keeping everything running smoothly: leader election. This process is essential for maintaining order and efficiency in environments where multiple processes need to work together seamlessly. We'll unpack how leader election functions, the challenges it encounters, and the different algorithms that have been developed to tackle these challenges. In a distributed system, having a designated leader is crucial. This leader acts as a coordinator, making decisions and ensuring that all processes are on the same page. But here's the catch. The leader needs to be active and reachable. If the leader fails, things can quickly spiral into chaos, resulting in inefficiencies and conflicts among the processes. To address these concerns, systems rely on leader election algorithms. These algorithms step in to identify a new leader when the current one is no longer functional, which is key to maintaining performance and minimizing coordination overhead. Although running an election round can consume resources, it happens infrequently enough that it doesn't significantly impact the overall system performance. One classic approach to leader election is the ring algorithm. So, how does this work? Each process has its own view of a ring structure, and when a leader fails, a process starts an election round by traversing the ring and gathering information from other processes. For example, if the previous leader is down, a process might skip over it and reach out to the next active node to find out who has the highest identifier. Interestingly, this algorithm can be adjusted to save space by only collecting the highest ranked identifier instead of a full list of active nodes. Thanks to the commutative nature of the maximum function, the last known highest identifier can be sent back to the initiating process efficiently. However, the ring algorithm isn't without its drawbacks. If the ring gets split into multiple segments, each segment might elect its own leader, which can lead to conflicts and a phenomenon known as a split brain scenario. This situation can create instances where two leaders operate independently, completely unaware of each other. To prevent this, a cluster-wide majority of votes is necessary to ensure that only one leader is recognized at any time. Now, while leader election is absolutely essential for the smooth operation of a system, it does come with its own set of challenges. The biggest concern is ensuring that the elected leader is genuinely alive and capable of fulfilling its responsibilities. To tackle this, failure detection algorithms are put to work, monitoring the leader's status and detecting any crashes. Without a reliable way to check on the leader, the system risks descending into disarray. It's also worth noting that a leader's identity can change without the processes being aware of it, which raises questions about how valid the local understanding of the leader really is. To address this, algorithms like the stable leader election algorithm combine the processes of electing a leader and detecting failures. They establish rounds with a unique stable leader while using timeout-based failure detection to maintain a consistent leader as long as it's reachable. Leader election is closely linked to consensus in distributed systems. Many consensus algorithms, such as Multi-Paxos and Raft, rely on a leader for coordination. Interestingly, the act of electing a leader itself requires a form of consensus, as all processes need to agree on who the leader is. Once consensus is achieved regarding the leader, the same principles can be applied to reach agreement on other system matters. In situations where multiple leaders might emerge, certain algorithms are designed to swiftly resolve conflicts. For instance, in Multi-Paxos, only one of the conflicting leaders can move forward, which is managed by gathering a second quorum. Similarly, in Raft, a leader can recognize when its term has expired, signaling the presence of another leader, and adjust its term accordingly. While having multiple leaders can enhance performance, it also introduces risks related to safety. To ensure liveness, meaning that processes can keep functioning if the current leader fails, systems must quickly determine whether a leader has indeed failed. Striking the right balance between safety and performance is crucial, allowing algorithms to enter a replication phase while effectively managing potential conflicts. In conclusion, leader election is a fundamental aspect of distributed systems, ensuring that processes remain organized and efficient. We've explored the ring algorithm and its variants, but it's clear that challenges like split brain scenarios and leader failure detection must be navigated carefully. Consensus algorithms like Multi-Paxos and Raft further highlight the intricate relationship between leader election and system coordination, emphasizing the importance of effective conflict resolution. As we continue our journey into the complexities of distributed systems, understanding leader election will remain a focal point. It not only boosts system performance, but also ensures that processes can adapt and respond to failures, preserving the integrity of the entire system. Thank you for joining us today, and we can't wait to dive deeper into the captivating world of distributed systems in our next episode.